Hey everyone, welcome. Just give a couple more minutes. People are still joining. So as you join, be logging into the Rubin Science platform at data.lsst.cloud. And when you enter the notebook aspect today, make sure you choose a large container. The notebooks, almost all of them will run with a medium container if you're already logged in, but if you're not yet, do choose a large container. And we've got a couple of announcements, so there's time to log out and log back in and choose a large container if you want to. Still seeing people logging in. So I'm just going to repeat that everyone who's here should be logged in to the Rubin Science platform at data.lsst.cloud, into the notebook aspect, and choose a large container when you enter. Since we did just update the notebooks that are in your notebooks/tutorial notebooks directory, some of you might encounter issues with them. If you had edited the notebooks in that directory and saved them, when we push updates to that directory, it can cause Git issues, and you might encounter errors when you try to open a notebook, such as a file load error. And if you do see that kind of error, we have a couple of ways for you to recover from it, sort of depending on your level of comfort with Git. We have a couple of options for you. So these options are in the slide deck for today, which I'm posting in the chat for people to access as they come in. I'm just going to go over them really quickly as well. There's detailed instructions on how to recover from these errors in the DP0.2.lsst.io documentation. So that's like the permanent fix is in the documentation there. It takes a little more time than you have right now before we get started to make that fix, but it's there for you for later. A faster fix is to simply, if you are familiar with Git, a faster fix is to simply make a new directory in your home directory, such as a My Notebooks directory, and then you can do a Git clone of all of the tutorial notebooks into that new directory. And then you definitely have the latest versions and you'd be totally ready to go for today. But that particular directory that you've just made will not receive future updates. So this option is really sort of just for people who kind of know what they're doing with Git and are comfortable with doing Git fetches, or who understand that this directory won't be updated in the future because it's one that you made, and thus you know to do the other fixes, like the longer fixes in the last slide. And then another really simple, fast, and temporary fix if your notebooks 04A or 04B won't open for you today is to just go to the GitHub repository for the tutorial notebooks, which is available at the URL here at left, and just download exactly those notebooks that you want for today and then upload them to the science platform. So again, these are all instructions only if you encounter errors opening your notebooks in the tutorial notebooks directory. If they open fine, you don't need to do any of this, but these fixes are there for you. They're in the slides, which I'm sharing again because I saw some people just join. And it's really this last option that's going to be the easiest, fastest fix for you today. And in the near future, we're going to be changing that directory to be read-only, so you'll never have these errors ever again, which will be wonderful for everyone. So I'm just going to pause there for a second to see if anyone has questions, anyone's unable to log in, anyone's unable to open notebooks 4A or 4B, need some emergency help right away. I can see the chat and we have lots of staff on hand, so feel free to just post in the chat if you're having trouble and we will help you. Okay, I'm going to continue with the announcements, but of course you can post in the chat whatever issues you're having at any time, even if someone's talking. So the only other announcement that we have today is just that the future delegate assemblies, we recently updated the schedule through September. You can find these schedules all in the DP0.2 documentation. Next week at this time is Stat Club as usual, since we alternate. There will be no assembly on Friday, September 2nd. It's the Friday of a long weekend, so everyone take a break. And then the next assembly after this one today will be Friday, September 16th, and we'll be doing notebook number 5, which is source detection and measurement, which is still the same as it was last year for DP0.1. It just points to DP0.2 data. And then we'll have breakouts that day as usual. So going back to today, right, as I said, we're going to do notebooks 4A and then 4B, or rather, Alex is going to present all of 4A, and then I'll pick it up and do as much of 4B as we get through within the first hour, and then we'll switch over to breakouts. So we'll come back to this page and we'll take your suggestions for breakout topics at around 10 a.m. and then we'll make the breakout rooms and everyone can go have a nice time working, hacking, chatting, what have you. Okay, I'm going to stop sharing my screen. Alex, you ready to, yeah.
Yeah, hopefully you can see my screen and it's showing the notebook. Is that right?
Yes, yeah.
Okay.
Okay,
great. Hi everyone. I'm Alex. I see a lot of familiar faces. That's great. I see a lot of new faces. That's awesome too. So I'm a member of the community engagement team. I'm a scientist at Fermilab and an assistant professor at the University of Chicago. Today I'm going to be talking a little bit about the Butler. And just to give you sort of some context, you know, so that you know how sort of my path towards getting the knowledge that I currently have, right? I'm not an expert on the Butler code development in any sense. A few years back, I started playing around with the LSST stack through something called the Stat Club, which was just a way for the community to engage with the LSST science pipelines. Over time, you know, we've assembled first through that process and then refined through the community engagement team a set of notebooks that hopefully are geared towards getting people started with the actual science pipelines mode for accessing data sets, which is known conventionally as the Butler. So the basic idea here is that we've written two notebooks at this point. One is intended to be an introductory notebook just to get you started to demonstrate how to access a subset of the data products that are available with DP0.2. And do some very basic visualization of those data products. To teach you just a little bit about why we use this thing called the Butler, what it does at a very high level, and also to get you familiar with the data products that are available in DP0.2. Okay, so I'll kick this off then. So the basic idea is that in the Rubin science pipelines, we would like as much as possible to separate the actual knowledge about where the data are located from the algorithms that actually work with and process the data, and from the users who are interested in doing science on the data. So for example, on the Rubin Science platform, which you're using now, it's a cloud-based implementation. And so the data itself is actually not stored on a conventional file system in the way that you're used to dealing with your local machine. It's stored on cloud data storage services called buckets, which you don't need to know anything about. But the idea is that because the Butler provides the interface to that data, you don't need to know where that data is actually located, what format it's actually stored in, or anything like that. if you know what data products you're interested in grabbing, you can just ask the Butler to give you those products, and you'll know what you'll be getting back, and you can use that and operate on it without ever having to know whether the actual data was co-located on the same machine that you're operating on, whether it was located on another machine somewhere else, whether it's a cloud-based file storage or anything like that. So that's sort of why we're using the Butler, what the Butler is intended to do. It turns out that there have been several iterations of the development of the Butler software. The one that we're currently in right now is called Gen 3. If you're looking through documentation online, you may occasionally see references to the Gen 2 Butler, which was the preceding version. For the purposes of DP0, you really only need to care about the Gen 3 Butler. So this is just context in case you're Googling around and happen to come across these terms. All right, so after some basic package imports here, we can move on to creating an instance of the Butler. So all we're doing here is importing some generic Python packages, importing the Butler itself from the LSSD science pipelines, and importing AFW display, which is the pipeline's display tools. And I think we've seen some examples of how to use those in previous notebooks. We're going to set some default matplotlib backends here. Set matplotlib as the default backend, and then try to adjust the figure size parameters. So with these imports done, we're ready to instantiate an instance of the Butler. So we would create an instance of the Butler that we're going to use to access the data sets. So in order to create an instance of the Butler, we want to provide it with two pieces of information. The first piece of information is a configuration file. It's basically directing the Butler to the data repository, the data set that we're seeking to access. It's a YAML file. The YAML is a sort of a markdown language. It's a human readable and machine readable, or human readable and machine parsable language. In our case for DP0.2, we don't actually need to point to any specific YAML file. We have this shorthand label, DP0.2, that we can pass to the Butler directly. And then in addition, we want to tell the Butler which collection of data within this larger data ecosystem we're interested in accessing. And in this case, we're going to specify, and essentially for all DP0.2 usage cases, we'd be specifying the 2.2i/runs/DP0.2 collection. Just for some background, 2.2i is just referring to the image simulation toolkit that was used to simulate these images. So you don't need to worry about this. At 2.2, it happens to be the version of the simulation run. And the directory runs here is referring to the fact that this is process data. All right, so with that in hand, we can create an instance of the Butler. Here are the warnings that you're probably familiar with in DP0.2. You don't need to worry about these. It's just some warnings about CFITS IO headers. So we now have an instance of the Butler available to us. If we want, we can look at the help string for the Butler and see, when we created our Butler, we passed it a config and a collection, but we could, in theory, pass it other different things when we created it. So the first thing that we're going to use our instance of the Butler to do is to access some DP0 image data products. For context, you can see a full list of the data products that, or a list of the data products that are available in DP0.2 here. These are sort of the high-level data products that we expect most delegates to be most interested in using. So there are processed visit images. These are single CCD, single exposure images. You see them often referred to as CalX, or calibrated exposures. And I think you've probably seen examples of accessing these in the past. There are deep co-added images. So these are images that are created from adding together multiple calyx, each in an individual band. So these, for example, will be a much deeper image of a region of the sky in I-band. The processing of co-added images are divided into tracks, which are larger units of sky area, and patches, which are smaller regions of sky area, which have roughly the same angular size as a single calyx or calibrated exposure. And then we have difference imaging process, difference imaging products, which are created from running the difference image pipeline on individual calibrated exposures. So these are intended to display time variable or transient source kind of analyses. So these are the image products for which the time domain analyses are done. In addition, and later in the notebook, we'll be accessing some catalogs. These are catalogs that are essentially derived from the different imaging data products that we saw above. So we'll come back to the catalogs a little bit later. So for our first example here, we're interested in getting this process visit image, this calyx. In order to do that, we're specifying a specific visit. So this is a specific instance where the camera was exposing to the sky, and we're grabbing a specific detector on the camera focal point. So we put this information together into what's called a data ID, and then we ask the Butler to get our calyx, our data set type, our calyx, that matches the specific data ID that we specified. So let's run this cell. And so the thing to note here is that we don't need to know anything about where the actual bits associated with this image live. The Butler is handling all of that for us. So the Butler is giving us back the data product that is associated with this specific data set. And so we can look at what that is. And we can see that what we've gotten back from the Butler is this exposure F object, which I think people are probably familiar with from previous tutorials. Okay. So how did we know what parameters that we could pass to the Butler to get a specific calyx? Well, in order to do that, we can look at the definition of this data set type. So the calyx data set type takes as inputs for its data ID the band, the instrument, the detector, the physical filter, the visit system, and the visit. It was enough to just specify the visit and the detector, but we could have also put in the band in here to grab that information. And we can also ask the calyx what band it is after the fact. So with the calyx in hand, we can just display it, and this is using code that we accessed before. I'm just going to make this figure a little bit larger. And you can see this is a region of the simulated sky corresponding to a single CCD on the simulated LSST cam focal point. And then just to save memory, we can clean that up and remove the calibrated exposure. So we can do the same thing for difference images. So here now, what we're going to be doing is changing the data set type to be a good seeing difference image exposure. And the data ID, you'll notice, is the same as the data ID that we used to grab the calyx. So this is giving us the difference image associated with this calibrated exposure. So again, we can ask the Butler to give us this data product, and we can visualize this data product. And you can see now that things have been cleaned up a lot. This is essentially differencing our individual calibrated exposure with a static sky template of this region. And we can see that most of the sources have been removed from this image. There are some residuals here that are either corresponding to real, variable, or transient sources in our image, or imperfect image subtraction. So again, we can clean up this image here. And then finally, we're going to access a Coad image. Just as a reminder, the Coad images are created from combining multiple process visit images. So they go deeper than the individual process visit images, and they're subdivided into tracks and patches. And so instead of specifying a visit number and a detector, we need to specify a tract and a patch, as well as a band, to get us back our deep Coad image. So let's do that. Sorry about the background noise. Hopefully Zoom is filtering it. We can hope. So, all right, we asked the Butler to give us a deep Coad, and it has. It's returned this Coad image. The Coad that it returned to us is also an exposure F data product. Actually, as also was F image. And so here we can plot it in the same way that we were plotting the calibrated exposure itself. Here we see a beautifully deep co-added image where we have a really rich galaxy cluster in the lower left-hand corner. So we can clean that up as well, just to save space. Okay, so we've shown how to access images through the Butler. I guess I'll pause here for a second. I'll check the chat and then see if there are any questions about image access there. So I'll just stop here for a minute in case there are questions. I'm not seeing any hands. And I think the comments in the chat are not questions. So I'm going to push forward then with Butler table access. Okay, so before going into this section, I'll just emphasize that the preferred technique for accessing the DP0 catalogs is through the table access protocol, the TAP surface. And there are tutorials that show how to do that access. However, you can use the Butler to also provide access to these data products, which is sometimes convenient if you want to access a catalog that was derived from a specific image or a process visit image. So I'll demonstrate how we can access several different catalog data products that were described in the DPP. And so these are catalogs here that essentially match up to the imaging data products that we just saw how to access. So you can see a description of these catalog data products available here. I'm not going to go through this in detail, but you can read more about it. So the first thing that we're going to do is access the source table, which are astrometric and photometric measurements for sources detected in an individual process visit image, an individual calyx. To access this, we're going to provide the same data ID information, the visit and the detector, that we used to access the calyx itself. So what we're changing here is the data set type. So now we're asking for the source table rather than the calyx itself. So let's do that. And you can see what we've accessed is a catalog of roughly 2,500 sources. And if we want to see the information associated with those sources, we can print the source table here. And you can see that the source table has each row is corresponding to one source that was extracted from the image, and the columns are photometric and astrometric properties associated with that catalog source. So the RA and the DEC, for example, you can also get flags for shape measurements and photometry, the band. So this is an I band image, and a whole lot of other information. All right, let's clean up that catalog. We can also access astrometric and photometric measurements for sources that were detected in the difference image. So the thing to note here is that the DIA source table groups together all sources detected in a single visit. And so the detector number is not used in accessing this image. So basically, as you could see in the difference image that we downloaded before, the number of sources is much smaller. And so rather than storing the sources on an individual detector level, we're storing them all for an entire LSST CAM focal point. So let's go ahead and access the DIO source table. So here, all we're specifying is the visit itself. Okay, and so here we've accessed 11,000 DIA sources. There are about 200 detectors on the DCAM, on the LSST CAM focal plane. So if you were to divide this 11,000 by 200, you would get roughly the number of sources that are detected on each detector. And you can see that that'll be much smaller than the 2,500 sources that were detected on the calibrated visit image, the visit image. So let's go ahead and see what the DIA source table looks like. Again, you can see there's some source ID. Each row is corresponding to one of these DIA difference image analysis sources, along with photometric and astrometric properties of these sources. We can retrieve sources from a specific detector if we're interested in it by selecting a subset of these sources that were returned through our query to the DIA source table. So you can see if we are selecting just our detector 175, then we're left with 49 DIA sources that were found in that detector. And we can display that section of sources again. All right, so we'll clean up that source table. And then the next set of catalog objects that we want to access is the objects that are detected on the Coad images. So these are objects assembled across the set of Coad images in a specific patch for all of the bands in that patch. And so in contrast to the catalogs that we were accessing before, where we only had I-band photometry, we'll now have multi-band photometry for the sources that are detected in the Coads. So again, we're going to specify a specific tract and patch. And so this is an area of sky that's roughly comparable to a single LSST CAM detector. And here we now have 37,000 sources available. And you can see photometric and astrometric properties of those sources. And then just to show, right, we have U-band flux as an example here, but indeed we have fluxes and photometric properties for all of the bands in which this region of the sky has been imaged, so U, G, R, I, Z, and Y. I'll go ahead and delete this catalog. And then we can also access summary parameters for DIA sources for a sky location. All right, now it's getting really loud, maybe too loud.
Yeah, your filter's doing an okay job of like suppressing it, most of it, just suppress and distorting it, but.
Yeah. So let me see if I can finish before they start pounding on anything. So we can also access DIA sources associated with a tract rather than with a visit. And so we can do that again here. And we get a large number, 280,000 DIA objects associated with a tract. So we can see those here. And then I think this is the final cell here. So we can also access force source photometry. So force source photometry refers to the process of fitting for a source at a specific location in an image, regardless of whether or not that source was detected in that image. And so as an example, you could imagine the case where you detect a source in the deep Coad image, but then you want to try and measure it in each individual image that went into building that Coad. Another case where this is useful is if you're wanting to look for dropout sources, they'll be detected in a Coad image, but may not be detected in an individual band. All right, so let's go through and try and do this. The thing to note here is that the force source table can be quite big. And so this is a cell that Bob thankfully pointed out was not running on medium-sized containers, so it's commented out for now. And instead, we're going to access for force source, the force source table just on the DIA object table. So the DIA object table is a smaller subset. So we can access that there. Already you can see this is a big table, so 2 million DIA force sources here. And you can see that there is astrometry and forced photometry provided for these sources. So, okay, I think the construction is now gonna cut me off, but hopefully I've kept to roughly half the time, which is good because it gives Melissa time to go through the intermediate Butler tutorial notebook. Hopefully this has given you enough information to sort of get started with accessing the high-level DP0.2 data products. So thanks for your attention. Sorry again for the background noise.
Thanks, Alex. I'm impressed the baby stayed asleep like all through the construction. That's great. It's a good nap time. Yeah, so yes, thanks for presenting O4A. And in the chat, I was just noting that if you did start things up with a large container, go ahead and uncomment those cells and execute them, and you'll see it's like, I forget, it's a lot of sources that are returned from that one. I forget the exact number, but like millions and millions. Yeah, Alex, you can try running it, and so people can see. I forget how many you get. And I did want to say too, if you are in a medium container and you try executing these cells, it'll stop your kernel. So you'd have to go back to the start and rerun your whole notebook. But aside from that, you're not damaging anything about the RSP by crashing your kernel. There's no like long-term damage. It's not dangerous. It's just annoying because your whole thing will stop and you'll have to go back and import your packages and everything. So don't be nervous about trying big searches. Go right ahead and try to, pull down millions of objects, or so what, 17 million forced sources in one patch. Yeah. So that's a lot. So that takes a large container. I'm just gonna pause again, just for any questions about container sizes or retrieving data before we switch to O4B. Okay, I don't see any hands up or hear anyone unmuted or see anything in the chat just yet. So I'm going to share my screen. Okay, so notebook 4B. We call it a more intermediate level because we're going to show you a little bit how to kind of browse around in the Butler to see what's there. So how to discover what data exists. And then we're also going to show you a little bit about how to apply constraints additional constraints on a Butler query, such as spatial constraints that aren't just tracked and patch, and temporal constraints, so that you can, like, for example, get visits just within a certain date range. So if you've got O4B open, oh wait, I lost my chat. I want to see it. There we go. Okay. So you've got O4B open, we can go straight to the package imports and creating an instance of the Butler that Alex just told you about how to do. We get that same warning, which will go away in the near future. And then the first part in section 2 is telling you a little bit about the Butler registry. So the data that's in the Butler is organized by collection and data set type and data IDs. And the data IDs you've heard about before. The collection you sort of already know because you always use it when you instantiate the Butler, and it's the collection for DP0.2. And if you were with us for DP0.1, you know that there's a different collection for DP0.1. So the collections are like a data release a little bit. So we can set up this registry and prepare to sort of query the Butler for what it contains with this cell where we set registry equal to Butler registry. And from there, we can use the query collections function on registry. And for DP0.2, I'll show you, you don't need to execute this cell, but I'll show you what happens if I just ask what all collections are even available within the Butler. This would be a natural exploratory thing that users might want to do. But for DP0.2, right now, as I say in this risk reminder here, there's really like no read-write restrictions on the Butler. So when you do this and you say, I want to see every single collection that exists, you see every single collection, all this the staff intermediate processing, every other delegate, if they've put stuff into the Butler and they've been doing some processing, you really see it all. So this is a useful little piece of code for the future when what's stored in the Butler registry is a little more limited. You won't be able to see other users' data in the future, of course. But for now, just because of the nature of DP0.2, it says, you know, everything's in production and in development, you can really like see a lot. So just looking for everything isn't that useful right now, but we did want to show you that you can do it. Instead, if you sort of know your collections, you can do that same loop over querying collections and just look for certain ones that you're interested in. So for here, DP0.1 and DP0.2, this cell's basically just showing you that they exist. If you are working together with other people and you know their username, and for example, if I said, oh, I made this really cool like co-added image where I just took like this 1 month of data and I co-added it in the I-band, and I've made it and now I want to share it with you. You could go and find it by looking for everything that's in my own collection in the Butler registry with this command here. So now I'm only printing the collections that are mine. So you could do this also for your own too. If you're like, oh, do I have stuff that I put in the Butler? Where is it? What did I name those things again? This is how you do it. So that's a little bit about how to use the Butler registry to discover or list the various collections that exist. The other thing that we expect users to want to be able to query or explore within the Butler are the data set types. And so you've learned a little bit about these in Notebook 04A with data set types like the deep coad, the calats, and the good seeing the difference images, and then the various catalog table types. You can also get at these data set types that exist for DP0.2 by looking at the documentation, which is what Alex showed you. But we also like to provide like another way to explore what data exists in the Butler by just printing out all what data set types are available in the registry. So again, like above, where I printed all the collections, this was commented out because printing all of the data set types that are available really gives you way too much, way more than we expect delegates to be interested in. There's intermediate steps. There's log files from the processing. There's reference catalogs. There's all kinds of stuff that technically is a data set type and is available, and you could access it if you want. But in the future, this will be a much more pared down list of just data set types of interest for science, like science ready data, basically. So we wanted to teach you how to query for all data set types, but it's not a super useful thing at the moment. Instead, we think it's more useful to apply search terms when you're querying the data set type. So if you're doing a project and you just sort of want to know, what all object catalogs, so what all source catalogs can I query if I only have the tract, for example. So now you want to look for all data set types that have that underscore tract in their data set name, which indicates that they're queryable by just a tract ID. And so I could do this and I get just a short list of catalogs that have that underscore tract in their name, which means I could search them by tract. There's another option here to list every kind of data set type that's associated with a deep coad. I will skip that and show you what happens instead if we don't have that wildcard there and we just look for data set types for deep coad. I thought I did. Hold on a second. We changed this like this. I wanted this to print like something like this to show what the data ID is. That's not what I want.
Melissa, I think you want the singular rather than query data set types, or
you want get data set type in there. Rather than query data set types, it should be get data set type.
It should be like this.
Yeah.
Yeah, without the S on the end.
Oh, thank you.
Yeah.
But why up here did we use query data set types and we get to see
Because
like what the data ID is?
Query data set types matches multiple data set types. So you've got a wildcard star underscore tract and you get an iterator, which you print out the data set type each time. Get data set type, you've got a single data set type you want to query and it doesn't return an iterator or anything because there's just one answer guaranteed. So you do get exactly that line, the deep coad band sky map track patch. Yeah,
my question is more like why when the command is this, because
it returns an iterator and you're printing the iterator. You'd have had to do next dt underscore deep coad and it would have then retrieved the first element from the iterator.
Oh, like if I did this and then this, does that get me what I actually wanted?
Yeah, except get data set type is what you should always use if you only want one answer.
I see. So using the next gets me what I want, but that's not best practice for the Butler.
Yeah, because you only want one answer because you're not using a wildcard in that parameter. It's just this fully qualified string and it will do an exact match on that. So.
Right. Okay, yeah, this is what we had before. And then you'd pointed out that using next is not the best practice. So we actually want.
Because you only want one answer and it's guaranteed to only give you one answer. So.
Right. Okay, so we actually do this different situation, and I had been trying to use the same sort of code. Okay, someone taking notes today?
Yeah, I got this.
Okay, you got that? Okay, learning on the fly. That's what Data Preview 0 is all about. It's great. Okay, yes. So the point I was trying to make is, in this case, it's the deep coad that you want to deal with, and now you want to see what its data ID takes. This is how you do it. And it was here, and now this is like not going to work. Yeah. So Alex, this is where if I hadn't changed this would have shown this, but now we just need to remove this. Let me make a note. Okay, wonderful. Moving right along to more about the data ID. Right. Okay, so another way to learn more about what the data ID is, or like what dimensions a data ID takes for a certain type of data product, is you can get the data set type like we did above, and you can print just, it's this one here, the dt.dimensions that's giving you the data ID here. So that's sort of like similar to what we already did above. And in this case, we define that we want a CalExp, and we define the data ID using the visit and detector as we did in Notebook 04A. All right, and then we go ahead and I forget what this is doing. It's just showing you how the data ID, you can get it from the data set refs, and then you can, if you ask to print it, you will see a truncated version. But if you want the full data ID for the thing that you've just asked for, you can see here, all we've done is specify visit and detector, because that's like the minimum amount of information that you need in a data ID. But the full data ID actually also includes band, the instrument type, and like some other ways to say band and visit as well. But of course, a visit is just one observation in a given filter. So you don't ever have to specify both visit and band, because a visit implicitly defines a band. Only one band was used for that visit. And you can see here as well, if we know the visit, but we don't specify the detector, then when we do this query, we're going to get all of the detectors associated with that particular visit back here. And so we've truncated the list a bit, but it will have found 187 detectors. Yeah. Okay, and so the next step, so far we've just been sort of querying the metadata for a given data set type and for a given, in this case, like a given visit. But in next step in 2.3, we're actually getting the image just using the data set reference that we had defined above. So what this loop is going to be doing is actually getting each CalExp for each detector that we had found was associated with that visit. And here, of course, we truncate it because we don't actually need to return every single CalExp. But if for some reason you did want to, as you're returning the CalExp, you want to display every one of them, you could uncomment this cell. And it's doing the same thing where it's getting the CalExp, but then it's showing each one. And we've put in a break here so that it doesn't do too many. But you can uncomment this and it will go ahead and show you each of the CalExp that it's returned from this particular visit. Sylvia, I see your question about, is there a notebook showing how to write user data in the Butler? Yes, we've got some notebooks in development that show you how to reprocess images. And if you're doing image reprocessing, basically the easiest / recommended / only way to do that is to be using the Butler to retrieve your images, reprocess them, and then write them back to the Butler. And in that case, you would end up with a user directory in the Butler named for your username. Those notebooks aren't ready yet. It's actually pretty complicated to do pipeline tasks within the notebooks, but it's something we're currently working on. Okay. So this part in section 3, this is where I really wanted to get to today with how to do some more specific queries. So in 3.1, we've set up sort of a basic image query. And in this case, it's only slightly modified from what we were doing before. Before we were saying, oh, we want CalExps of a certain visit and a certain detector. And now here we're modifying that and saying, well, I want CalExps of a certain detector, but I want them for any visit between visit number 192,000 to 193,000. And so you can say, I want to know how many how many visits there were within that range. And so this is useful if you have already maybe used the CCD visit table to identify visits of interest for a given time range. We're going to show you how to use actual times instead of visit numbers to do your temporal query below. And the cell that's being skipped just does very similar to what we did before and just displays retrieves the cal-exps that you've just found and displays them. Before we show you how to do temporal and spatial searches, this section 3.1.1 shows you how to get temporal and spatial metadata from the dataset refs themselves as sort of a first step. It's important if you're going to be using or applying temporal and spatial queries that you sort of understand how to get that information out of the images and out of the Butler to begin with. So these steps just go through for the data set refs that we identified above, which was from this query here, where we're looking for a certain number of visits. You can, instead of doing a butler.get and retrieving the cal-exp like we've done before, now we're just retrieving and printing the visit info. And visit info has things in it like date, exposure time, air mass, the pointing, coordinates on the sky, that kind of thing. So this cell is printing everything that's in visit info. But if you knew that you just wanted date, exposure time, and location on the sky, you could just print out just those things for a given set of visits. So here we're just printing some metadata for visits. And then the next example is printing more metadata, but in this case, we're using the world coordinate system associated with a cal-exp to print the corners. So we use the bounding box for that particular cal-exp, and then we use the WCS to just print out the 4 corners, which is just sort of a handy demo of how to use the spatial metadata that's associated with a cal-exp. So as you can see, doing this is a little bit slow because you're querying the Butler every time and you're getting that the bounding box and the WCS for each cal-exp as you go in this loop. Okay, thanks. Just noting the questions in the chat being answered. And there's actually a faster way. So here, this is a similar query on the data sets as we did above. Then we've added this dot expanded to the end to get a little more information. And that lets you retrieve the same sort of exposure time, bounding box, etc. information. It's just a lot faster. So you see that was like instantaneous. So when you're doing these kinds of queries and you want to get image metadata for a bunch of images, it's actually a lot faster, but just a little less intuitive to use this second way. So that's why we want to show you first sort of the slow, intuitive way, and then show you this faster way. All right, moving into making putting temporal constraints on your image queries. We want to start by getting the visit info for one cal-exp of interest here, which we've already done before. So you've seen that before. And then we want to use that time that when that particular visit was obtained and make a time span. So maybe you've been really into this particular visit and you've been looking at it. Now you want to know what all visits were obtained from 10 minutes before to 10 minutes after. So you're setting up the particular time of your visit of interest, and you're defining that a minute is 60 seconds. And then you basically define a time span that goes from 10 minutes before to 10 minutes after. In this example, we've used as our time of interest, we've gotten that time of interest from a visit, but you could also just user specify whatever your time range is. You don't have to, use a particular visit to identify your time span. So but in this case, we do use a particular visit to define our time span. And then the way you're putting that query into your Butler call is here, where anywhere where a particular visit overlaps your time span that you've defined above as this right here. And so we can look for all data sets that match that. And then here we're printing the data IDs of those ones. And we can see that we found 1,600 CalExps that overlap. But remember, that's 1,600 detectors that were obtained, not visits. So each visit has about 187 detectors. So it's not the number of unique visits that were in that time range. So instead, to just get the number of unique visits, we can do that by just using the NumPy unique function to find the unique numbers of visits. And we find there were 13 unique visits in that time span. So that's how you would identify, visits if you wanted to just get like sources that were obtained in a certain month or whatever your science goal is there. Okay. So in the last couple of minutes, let's cover section 3.3, which is doing spatial image queries. The first little example here in 3.3.1 is how to get, if you already know the location that you want to query at because you already have like the CalExp, and now you want to get deep Coad, the deep Coad that overlaps with that CalExp. So in this case, it's like overlapping images where you already know where one image is. That's pretty straightforward. And that's what you start by grabbing the visit info for the CalExp that you want, and then you can go get the deep Coad that matches with the same data ID. And here you can see that the deep Coads that overlap with that particular visit. So that's one way, but then we also want to show you how, if you just using like a user specified right ascension and declination, you can also find overlapping images. And in this case, we're using the HTM, what's it stand for? Higher something. Where is it?
Hierarchical triangular mesh.
Thank you. Oh, here it is. Yeah, right here. Yep. And it's just a way of dividing up the sky. And HTM grids, yeah, thanks. I always forget that acronym. Come with a level that kind of gives you the resolution of areas with which you're dividing up the sky. And so for this example, we're just choosing a level of 10. And in this case, we're not just sort of saying any right ascension and dec, but like in the other examples, we're using the information that we get from a given CalExp of interest. So we're using the visit info again to define our RA and dec, but here you could just put in whatever arbitrary point on the sky, well, within the DC2 footprint that you wanted. So we define a right ascension and declination, and then we use the HTM grid that's already defined. And so you can see that here, using a level 10 means a circle of radius about almost 300 arc seconds on the sky. So that'll be sort of the size of the area that we will be using to say, okay, this is my location. That's the size of the HTM grid point. Now I want to get all CalExp that overlap with that circle on the sky. And so it's up here where we've defined the HTM ID that gets passed into your Butler query. And in this case, you could just have this and just ask for the spatial, just do the spatial query. But since we already have defined that time span query from before, this is actually doing both a temporal and a spatial query at once, and just returning the 3 CalExps that happen to overlap both in time and in space with the user specified RA and dec and user specified 20 minutes time range. So from here, the last step in this one is just to do the same thing, but on catalog data instead of images. But that covers what we wanted to show you today, a bit of exploring the Butler and then doing spatial and temporal queries when you're using the Butler. So I'm going to stop there. We'll take some questions and then we'll set up some breakout rooms. I don't see any hands raised and no new questions in the chat. I'm just going to give it another minute, since you're probably playing around with some stuff. Yeah, Louise.
Yeah, okay, so if I'm wanting to do a general like catalog information search, I should use the tab. But if I want to search catalogs specifically anchored to a specific image, then Butler's what I should do.
That's how we think of it. Yeah, it's tap suits most of your use cases, and you can also search tap by specifying a visit ID as well, depending on which catalog it is. But you're right that in the case where you've got your data ID and you've got your image, it can be fast to just say, okay, now give me all the sources that overlap that image. Butler is your friend there.
But it's the same catalog info that is available, right?
It's all the same data. Yeah, just sort of packaged up and queryable in different ways.
Yeah.
Yeah.
Okay, great.
Yeah.
Thank you.
Okay, in that case, let's make some breakout rooms. And as always, main room will be open and staffed for a general Q&A about literally anything. So if you wanted to stick around, and I'm going to turn off recording because we don't need to record the rest of this.